Okay, so our next speaker is Armand Dua from Oklahoma State University. He's going to tell us about non-equilibrium universality.
Thank you. Yeah, so I'm Armand Dua. I'm a final year PhD student in Dr. Bitovsky's lab. So today I'm excited to talk about non-equilibrium universality in squeezing phases. So in this work, we show universal scaling and therefore a dynamical phase transition that has application in sensing and quantum simulation in parallel interacting spin systems. So parallel interacting systems are some of the most promising platform where you can really controllably investigate many-body non-equilibrium dynamics, highly entangled states. And in particular, if you think of spin squeezing, then it has already been realized in various parallel interacting systems such as Rydberg arrays and trapped ions. So then a natural question is that can we, if we're looking at these non-equilibrium dynamics, can we can we investigate these things in terms of phases? There's already promising work which kind of shows that it makes sense to think of this dynamical generation of entanglement in terms of phases. For example, in this work, the authors have shown that in the S-collective regime, where you have scalable squeezing, you can connect that with the thermalization of that state into a long-range order. Very recently, there's been work where it has been directly shown that there's a correspondence between the scalable squeezing phase and XY ferromagnet. So this also shows a direct sort of connection between the scalable squeezing phase and long-range order, thermalization to long-range order. And very recently, it has also been shown that you don't necessarily have to have thermalization to long-range order. You can have sort of a quasi-long-range order. If you have a critical slowing down, then even for that quasi-long-range order, you can have scalable squeezing. So what we really wanted to look at is that what if we look at the non-equilibrium dynamics and try to identify some dynamical phase, some genuine dynamical phase? Can we do that? And what I will try to convince you guys in the rest of the talk is that we can. So let me very briefly introduce the system that we work with. So we have a bilayer system with square lattice, with parallel interacting spins, and the model that we work with is the following. So previously we showed that this model can generate scalable squeezing, and the way it does that is through this interlayer spin exchange term, which creates these entangled pairs of excitations, which gives you two-mode squeezing in mixed quadratures, and let me show that really briefly here. So we have these sort of mixed quadratures where we get a squeezed quadrature and the anti-squeezed quadrature. We obviously work with the squeezed quadrature. So as a first result, let's see how the time evolution of the variance of this squeezed quadrature looks like. So let me unpack this figure. There's a lot here. So we're looking at the variance of this squeezed quadrature for a number of systems. So with increasing opacity, we have larger systems. And we have kind of divided it into two different regimes. So we can work with small. This is the aspect ratio. So AZ is the layer separation, and L is the side length of our lattice. So the aspect ratio is AZ over L. So we have looked at a small aspect ratio for which we see that the minimal variance increases with system size. So there's a system size dependency. But if we work with a large aspect ratio, then we see that the minimal variance pretty much remains constant around a value of 1. And I'll get in a second that why we choose AZ over L as a control parameter. So this then begs the question that, okay, so how does the transition happens between these two dynamical regimes? So to do that, we sort of map out the dynamics. That's what we have here. So we look, we vary the aspect ratio. We look at different parallel exponents. And we clearly see that there are two dynamical regimes. And there's a transition happening here. And we define them as fully collective regime. And the way it's defined is that in the fully collective regime, the variance is always around 1. It does not change with system size. Whereas in the partially collective regime, the variance sort of increases. And the bigger your system is, your minimal variance keeps increasing. That's how we define it, and the yellow markers are showing the sort of the critical AZ over L, and it's very easy to extract those if you just plot, this function, that how the minimal variance is scaling with the number of particles or system size, same thing. equivalent things. So we see that in the collective regime, fully collective regime, there is absolutely no system size scaling at all, but then a transition occurs. So this then corresponds to this transition. So now, having clearly shown two distinct dynamical regime, let's move on to scaling, because that's how we will eventually try to convince that there is actually two dynamical phases. So first of all, let me just briefly try to explain that why we choose the aspect ratio as a control parameter. So it's very clear to see that we need increasing values of the layer separation as we increase our system size. Again, with increasing opacity, we have bigger systems. So that gives you an intuitive idea that you have to rescale AZ with L somehow to get a sort of a divergent, sort of a convergent transition. And it turns out this scaling is very simple. If you just rescale it with AZ over L, we see that all these transition points converge into one point. There's a little bit of discrepancy here, but that's coming from the finite size effect. For larger systems, we see that they match quite well. So this is then the transition point. We have a collective phase, fully collective phase. We have a partially collective phase. We can do a second rescaling here in the y-axis. That's what we do here. We will come back to this exponent later, but for now it's just an exponent, and if we do that, it works wonderfully. All the curves just collapse into a single curve, which is pretty impressive, but so we have a full collapse of the minimal variance here. But what is probably more important here is that in the partially collective regime, this follows a sort of exponent of a power function of the control parameter. So this already gives you a clue that, okay, there's probably some sort of scaling that we can get out of this. And so let me just jump right into the scaling, the full scaling of the full time dynamics, starting from our scaling ansatz. So this is our complete scaling ansatz, which takes into account all the important system parameter, like the layer separation, the number of spins, and we scale our variance. This is not the minimal variance, this is the time-dependent variance. And we also scale the time with those parameters, layer separation, number of particles. T minimum corresponds to the time that corresponds to the minimal variance. So if we do, this is really just giving away the full result of our work, but we will relate to it to the previous figure by the end of this talk. So what we see here, let's start with the inset. So the different lines correspond to different n. So what we have done here, that we have rescaled, but we have only rescaled with the layer separation. There is no n rescaling here. So if you compare with the equation, we are not using this. We're just using the layer separation. And as a result, what we get is that it's hard to see here, but in each line, it's all the different AZ curves sort of collapse into each line, which correspond to different n. But if you then again further rescale it with the n-dependent term from our full scaling ansatz, then we get just one single curve. So this has all the different AZ, all the different n, but we end up with just one single curve. So this is the full universal scaling collapse. So let's sort of unpack from here again. So instead of looking at the full scaling collapse, what we can do is step by step is that we can think of fixed system size from here. So for fixed system size, you'll notice that these are just constant terms, and they can just be absorbed into this function. And this is now the new scaling, sort of the constrained scaling function that we have now. And the plot corresponding to this is the, sorry about that, is the following one. So in the inset, we have like raw data. There's no scaling whatsoever here. And we see that the variance has different curve corresponding to different AZ. The minimal variance reaches late and late with increasing AZ, which makes intuitive sense. But then if we do this rescaling, they all collapse. This is not new. We saw this in the inset of the previous figure. And this corresponds to one of the n values of the previous inset. But finally, we're going to go even more specific compared to this. So we're going to go to this case where we want to look at the minimal variance. So if we are thinking about minimal variance, then this term becomes, sorry, this is misbehaving. This is the slide that I want for minimal variance. So for minimal variance, we have that this is 0 because the time is now the t minimum, and we end up with an incredibly simple scaling function. which looks like this. And this is exactly what we saw in the first figure where we had the red curve. We saw that the minimal variance, just you can scale it with L to the power minus 0.55, and this was that 1.25. So let me go back to that figure again. So what I show here is that these two exponents, they just appear out of the full universal collapse. They are not a separate part of the way that we are rescaling and the way that we're rescaling based on how we are defining the phase transitions. So that's really the second last slide. So as a summary, we show two dynamical squeezing phases, and we sort of established that these are true dynamical phases because we have identified a universal scaling. And as an outlook, work has already been done for the short-range Heisenberg model case, but we have done it for parallel interacting cases, and it would be nice to see if there's a connection between these two. I think I'm out of time, so I'll skip the thanks. I'll take any questions if you have.
Time for one question.
Thanks, Armand, for the talk. On slide 6, you showed a plot, and there was some, I think you had statistical error bars that were a bit big. And
Oh, yeah.
if you can,
These are
comment on
pretty.
that, yeah.
These are pretty large, and
Could
yes.
there be any underlying shape in that region, or?
No, the reason is that in this region the values themselves fluctuate a lot because the values are very small. So a fluctuation from, let's say, 0.8 to 1.2 shows up as really big fluctuations, but the actual values are not so different. So that's why we can actually rely on this to be pretty much around zero.
Okay.
Yeah.
Great, thank you.